Hello, good morning, and welcome to the lecture series on numerical analysis. So basically, numerical analysis is a mathematical course for engineers and scientists. It is designed to provide mathematical procedure for determining approximate solutions of certain problems that arises in science and engineering. So this course is basically course on numerical analysis, and it provides the theory and applications of numerical methods which help us to determine approximate solutions of problems such as an evaluation of definite integrals or solution of linear or non-linear order differential equations or partial differential equation and so on. Such approximations are needed because analytical methods either intractable or the problem under consideration may not be solvable by analytical techniques. So in this series, first we define finite differences, which are very useful to define other numerical methods. So basically, let us consider this set of data values xi, yi, where I equals to 0, 1 up to n. It means we have a n plus 1 data points for any function y equals to fx, where x being equally spaced, that is xi equals to x0 plus ih, I run from 0, 1 to n. Suppose that we are required to recover the values of fx for some intermediate values of x, or to obtain the derivative of fx for some x in the range of x0 to xn. The method for the solution of these problems are based on the concept of the differences of a function, which we now proceed to define. So first we define forward difference. So let us consider x0, y0, x1, y1, x and y1 with the discrete data values of the function y equals to fx at n plus 1 discrete points. And let us consider the differences between consecutive values of arguments such as y1 minus y0, y2 minus y1, yn minus yn minus 1. These differences are known as differences of y, denoting these differences by del of y0, del of y1, del of yn minus 1 respectively. So we have del of y0 equals to y1 minus y0, del of y1 equals to y2 minus y1, and del of yn minus 1 equals to yn minus 1, where del is called the forward difference operator, and del y0, del y1, del of yn minus 1 are called first forward differences. Similarly, now if we take the differences of the first forward difference, then we find the second forward differences, and these differences are denoted by del 2y0, del 2y1, and so on, which are defined as follows: del 2y0 equals to del of y1 minus del of y0. Similarly, del 2y1 equals to del of y2 minus del of y1. And similarly, we can define higher order differences for such as third forward difference, fourth forward difference, etc. So thus in general, nth forward difference is defined by del nyi equals to del of n minus 1 of the first forward difference of yi. Now if we use the definition of first forward difference del of yi, which is equals to y of I minus 1 minus y of I, which is given by del of n minus 1 y of I plus 1 minus del of power n minus 1 y of I, which is the basically for first forward difference of del of n minus 1 yi. So now this table shows the first forward difference table. Forward difference table for of all order. Suppose we have given 7 data points x0, y0, x1, y1 up to x6, y6. Now the first forward difference is given by this third column del, where del of y0 is basically the difference between y1 and y0. It means del of y0 equals to y1 minus y0. Similarly, second entry of this column defines the difference between y2 and y1, which del of y1. Similarly, del of y2 equals to y3 minus y2, and del of y5 equals to y6 minus y5. Similarly, fourth column del 2 is defined the second forward differences, which is the basically differences of the first forward differences. So del 2 y0 is basically the difference between del of y1 and del of y2. It means del 2 y0 equals to del of y1 minus del of y0. Similarly, del 2 y1 equals to del of y2 minus del of y1. And in last, del 2 y4 equals to del of y5 minus del of y4. Similarly, third forward difference is defined by this one, which is the basically differences of the corresponding second order differences. Similarly, we can define del fourth order difference, forward difference, fifth order forward difference, or sixth order forward differences. Now next we define backward differences. So suppose same data points are given x0, x, y0, y1, y1, x1, y1, xn, yn. Now again, if we take the differences y1 minus y0, y2 minus y1, yn minus y1. Now these are called the first order differences if they are denoted by nebula of y1, nebula of y2, nebula of yn respectively. So nebula of y1 equals to y1 minus y0, nebula of y2 equals to y2 minus y1, and nebula of yn equals to yn minus. Keep in mind here that this difference is denoted by del of y0 in case of first forward difference. Now here it is denoted by nebula of y1 in case of backward differences. It means this entry is left with the negative sign. Or in case of forward difference, it is right with the negative signs. So this entry y1 minus y0 in case of forward difference is denoted by del of y0, while in case of backward difference it is denoted by nebula of y1. Similarly, this entry is denoted by nebula of y2 in case of backward difference, and this is denoted by del of y1 in case of forward differences. And last, this entry is denoted by nebula of yn in case of backward differences, but if in case of forward differences, this entry would be denoted by del of yn minus 1. Here nebula is called the backward difference operator. In a similar way, one can define backward differences of higher order such as del 2 y0, del 2 y2, del q y3, etc. Now, with the same values of x and y as in table 1.1, a backward difference table can be formed. X given arguments, x and y are the given data points. Suppose again same data points are given. So now the third column denotes the first backward differences. Del of nebula of y1, which is y1 minus y0. Nebula of y2, which is the difference between y2 and y1. And nebula of y6 equals to y6 minus y5. Similarly, fourth column denotes the second backward differences, which are the differences of the first backward differences. It means nebula 2y2 is basically nebula y2 minus nebula of y1. Similarly, nebula 2y6 is basically nebula of y6 minus nebula of y5. Similarly, one can define third backward difference, fourth backward difference, fifth backward difference, and sixth backward differences. Now, next we define the central differences. The central difference operator is basically denoted by delta, and it is defined by this relation. Same differences, the corresponding arguments. Suppose y1 minus y0 is denoted by del of y1 upon 2, y2 minus 1 is delta of y of 3 upon 2, yn minus 1 equals to del of yn minus 1 upon 2. Similarly, higher order central differences can be defined with the values of x and y, as in the preceding two tables, a central difference table can be formed. This one. So again, same. The third column defines the first central difference. Says so y1 minus y0 is basically del of y1 upon 2. It means average of two suffix 1 and 0. Average is 1 upon 2. Similarly, difference between y2 and y1 is denoted by del of y3 upon 2. Here index is basically the average of these two suffix 1 or 2. So 1 plus 2 divided by 2 is basically 3 upon 2. Similarly, del of y5 upon 2 and so on, del of y11 upon 2. Now this fourth column denotes the second central differences, which are basically the corresponding differences of the first central differences. So again, del 2 y1 is basically del of y3 upon 2 minus del of y1 upon 2. So again, here index 1 is the basically average of these two suffix 3 upon 2 and 1 upon 2, which is basically 1. Similarly, one can define third central difference, fourth central difference, fifth central difference, and sixth central difference. So from all the three tables, it is clear that in a definite numerical case, the same numbers occurs in the same position, whether we use forward difference, backward difference, or central differences. So thus, there is a relation between forward difference, backward difference, and central difference, which is denoted by del of y0 is basically nothing but nabla of y1 or delta of y1 on 2. Similarly, del qy of 2 is nothing but nabla cube of y5 or delta cube of y7 upon 2. Now, next we define the shifting operator. The shifting operator is defined by this relation E of yr equals to y of r plus 1, which shows that the effect of E is to shift the function values of yr to the next higher value yr plus 1. In general, e raised power plus minus n yr equals to y of r plus minus n. It means if we use positive n here, if e raised power positive, then it shifts to the right to the argument. Now, if we use negative power of e, then it shifts left to the argument. So if suppose r equals to 1, and if we apply this operator e over this y1, then it's shifted to the y1 to the right side. It means next point is y2. Similarly, if we use the e raised power minus 1 over the argument y1, then it's shifted to the left to the y1, which come to be y0. Now next we define averaging operator. The averaging operator is defined by this relation mu of yr, which is basically 1 upon 2 y of r plus half plus y of r minus half. Now some other relations between various operators which we have defined earlier. So we have del of y is not equals to y1 minus y0, which is equals to, now this y1 can be written as shifting operator over y0, because if we apply shifting operator over y0, then this is e of y0, which is basically nothing but y1 minus y0. Now if we take common y0, then it becomes e of minus 1 times y0. So therefore we can find here that the first forward difference of operator del is related by shifting operator with this relation del equals to e minus 1, or you can write shifting operator is equals to e equals to 1 plus del. We can now express any higher order forward differences in terms of the given function values. For example, it means higher order forward differences can be expressed in terms of function values such as y0, y1, y2, y3, and so on. Suppose we want to calculate del q y0. So basically, we know that del is related by shifting operator with this relation del equals to e minus 1. So if we substitute del equals to e minus 1 here, power 3 y0, and if we use binomial theorem here, so its expansion is given by this relation eq minus 3e square plus 3e minus 1 times y0. Remember here that e is our shifting operator. Now, if we apply y0 over these operators, so e cube y0 is basically nothing but y3. Similarly, e cube y0 is y2, e y0 equals to y1, and so on. So from the definitions, the following relation, we can obtain the following relations also. The apply equals to 1 minus e raised power minus 1. You can easily prove this one. Central difference operator delta is nothing but e raised power half minus e raised power minus half. Averaging operator mu is related by this relation with the shifting operator e. Similarly, averaging operator and central difference operator are related with this relation. Similarly, forward difference operator, backward difference operator, central difference operator, and shifting operator are related with this relation. Similarly, our shifting operator is related to the derivative of the function is by this relation e equals to e raised power hd, where capital D is nothing but derivative with respect to x. Now, let's see its applications. So first one, so that e raised power x times u0 plus x del of y0 u0 plus x square upon 2 factorial del 2 y u0 plus and so on. equals to u0 plus u1x plus u2x square upon 2 factorial percent. So to prove this result, we start with left hand side. So our left hand side is given by this relation. So now if we take u0 common out from this bracket term, so we get e raised power x times 1 plus x delta plus x square upon 2 factorial delta square plus and so on up over u0. Now this is our exponential function, which is given by e raised power x delta over u0. Now exponential these e to power x times e to power x delta can be written as e to power x times 1 plus delta del u0, which is now we know that there is a relation between forward difference operator and separating operator, which is given by e equals to 1 plus delta. So this can be written ex or eu0. Now again, if we expand this in binomial series, so we get 1 plus x e plus x square upon 2 factorial e square plus and so on over u0. Now if we operate u0 over each term, so we get u0 plus u1x plus u2x square upon 2 factorial plus and so on, which is our required result. So till now we have defined the forward differences for the discrete data values. Now if we are given a polynomial, then how to find the differences, either forward difference, backward difference, central difference, and so on. So let y equals to fx be a polynomial of nth degree, so that yx equals to a naught x to the power n plus a1 x to the power n minus 1 plus a2 x to the power n minus 2 up to constant term an. Now if we take the differences between two consecutive values of x, so suppose this is the value of the function y, this is the value of the function at the point x. Now if we take the next point x plus s, then value of the function is given by y of x plus h. Now if we take the values between two consecutive values of x, y of x plus h minus y of x, which is given by now a0 x plus h to the power n minus x to the power n with multiplication of constant. Similarly, second term will be a1 times of x plus h to the power n minus 1 minus x to the power n minus 1 plus and so on. Now, if we simplify this by using simple binomial theorems, we obtain this a0 and s x to the power n minus 1 plus a1 prime x to the power n minus 2 up to constant term an prime. Here, a1 prime, a2 prime, an prime are the new coefficients. The above equation can be written as, now this is our first forward difference of y, which is denoted by del of ix. So a0 and h x to the power n minus 1 plus a1 prime x to the power n minus 2 plus constant term an prime. This shows that the first difference of a polynomial of nth degree, it means we have an n degree polynomial, so its first forward difference is basically a polynomial of degree n minus 1 here. You could see here del of ix is nothing but a n minus 1 degree polynomial. Similarly, the second difference will be a polynomial of degree n minus 2, and the coefficient of x to the power n minus 2 will be a0 n times n minus 1 h square. It means coefficient of second difference polynomial of degree n minus 2 will be a0 n times n minus 1 h square. Thus, in general, the nth difference is basically nothing but is a0 n factorial h to the power n, right? Which is a constant term basically. Hence, the n plus 1 and higher differences of a polynomial of n degree. It means if you have an n degree polynomial and if you find nth difference as a constant term, then n plus 1th difference of a polynomial will be a 0. Conversely, if the nth difference of the tabulated functions are constant and the n plus 1 and n plus 2 differences are vanishes, then the tabulated function represent a polynomial of degree n. So it means if you have n degree polynomial, then you could find nth difference as a constant. Or conversely, if your nth difference is a constant function, constant value, then you will find a n degree polynomial. So the one thing is important here, that these results hold good only if the values of x are equally spaced. So till now we have defined that values of x are equally spaced, all the operators defined either forward, backward, central, shifting, or averaging operator, these will behave only the values of x are equally spaced only, right? So let us see one more example. Find the missing term in the table. Here x equals to 0, 1, 2, 3, 4, and corresponding y equals to 139 dash 81. It means there is a one missing term corresponding to x equals to 3. Now we have to explain the result is different 3 to the power 3 equals to 27. One could see that 13981 is basically a 3 to the power x function. Because if you put x equals to 0, then we get 2. X equals to 0, then we get 1 in the function 3 to the power x. If we put x equals to 1, then we get 3. If we put x equals to 2, then we get 9. If we put x equals to 4, then we get 3 to the power 4 equals to 81. So by this logic, this missing term should be a 27. But if we, since there are 4 points are given, it means 0, 1, 2, and 4, and corresponding values of y 139 and 81. So now that given data can be approximated by a third degree polynomial, because if we have n plus 1 data points, then these n plus 1 data points represent a nth degree polynomial. So here 4 data points are given, so corresponding function would be a third degree polynomial in x. So hence higher order differences must be 0 according to the previous condition, because we know that if n plus 1 degree differences of a polynomial are constant, then if nth difference is a constant term, then n plus 1 and higher order differences must be a 0. Or if conversely nth difference of tabulated functions are constant, then n plus 1 and n plus 1 differences all vanishes. Then the tabulated function represents a n degree polynomial. So here we are given 4 data points. So therefore these data points should represent a third degree polynomial in x. So hence del for y0 equals to 0. Now if we substitute this relation del equals to e minus 1, it means relation between forward difference operator and shifting operator. And if we simplify, then we get e minus 1 to the power 4 y is not. Again, if we expand by using binomial theorem, so it becomes e for y0 minus 4e cube y0 plus 6e square y0 minus 4e y0 plus y0 equals to 0. Now if we use the shifting operator definition, so y0 is shifted to y4, y0 is shifted to y3, y0 is shifted to y2, y0 is shifted to y1, and y0. Now we have the corresponding values, because suppose this is the corresponding value y0, y1, y2, y3, and y4. So here in this relation, y3 is unknown and remaining values are known to us. y0 is given by 1, y1 is given by 3, y2 is given by 9, y4 is given by 81. If we substitute these values in this relation and simplify, then we get y3 equals to 31, while y3 equals to 31. So the tabulated function is a 3 to the power x, and the exact value of y3 is 27. And this calculated value y3 equals to 31 is the approximate value of the data values. So the error is due to the fact that the exponential function 3 to the power x is approximated by means of a polynomial in x of degree third. So basically numerical analysis gives you the approximate values to the data points if you do not know the exact behavior of the function. So thank you for today's lecture. In the next lecture, we define the interpolation as an application of the finite differences. Thank you very much.